Know that at this time your blood will go down to the stomach. There's less blood on the up there on the brain. So never mind. I will have an activity for you later on to keep you awake. Now let's finish up on the gear first. Now we're talking about two interlocking gears. That means they mesh together. And you can see that when they turn, one, if you turn in the clockwise, the other gear must turn in the opposite direction, which is the anti-clockwise. Yes. You go ahead. All right. So, before lunch, I show you how to calculate the gear ratio, which I think that you know how to do it already. Remember, it's the number of teeth of the driven gear first. That is the numerator. Am I right? And the denominator is the number of teeth of the what? Driver gear. So bear it in mind. So we will have that one here, and that's how you calculate, and you get your gear ratio. So now that's only the gear ratio. But so far, we're talking about the speed. How about the rotating speed? Because the thing will rotate, right? So therefore, now we look at the speed of the rotating gear and see how to do that. Now, of course, you know which one will go faster, which I asked you already. Which one will go faster? This one, am I right? Because this one, when make one round, this guy will make how many rounds? 1.5 rounds. Very good. Well said, okay? Now we'll talk about the rotating speed. How do we measure it? It's always measured in terms of what? Number of rotations per minute. It's always per minute. Okay? How many times it will rotate per minute, in other words. And of course, in short, we use RPM to stand for rotations per minute. Fair enough? Now, so these are terminology here. Okay, now you are saying that this one, now, rotate, which one is a faster, by the way? A or B? A faster, right? Okay, A is faster. How fast? That's the one. Can we calculate how fast it is? Or what's the speed of the gear B? So that's the kind of a thing we want to know. Now, there's a very, very nice formula for you to calculate the rotating speed of the two gears when they interlock together. It's quite straightforward. Now, watch out carefully. The speed of gear A times the number of teeth of gear A. Same. So, speed of gear A times the number of teeth of gear A is equal to the what? The speed of gear B times the number of teeth of gear B. Simple enough? Okay, it's a very straightforward equation here to calculate. So in other words, I can calculate the speed of any gear given one of them. If I know the speed of A, I can find the speed of B and vice versa. All because of this one little formula here. Now let's see how to use this little formula. Okay, now you can also write in a different way, express in a different way. I can write out, for example, the speed of gear A over the speed of gear B is actually equal to the what? Number of teeth of gear B divided by the what? Number of teeth of gear A, right? If you move around, this equation here, you will get this equation here, which is a fraction, all right? Expressed as a fraction or as a ratio. But we know what that is. That is our gear ratio. Because my gear B is the driven gear. And my gear A is the driver gear. So I can say that this one basically is the gear ratio. Now, in other words, I can use the gear ratio to find the speed of gear A or gear B. Okay, now let's see how to do it. There's some technical problem here. Oh, battery. Okay, good. So now we can express the speed of A and B, the gear of gears A and B in terms of the gear ratio. Now that's how we do it. Suppose gear A, the road speed is what? 90 RPM, rotations per minute. What is the rotation speed of gear B? Now, we simply use this one here, right? So we know that gear A is what the speed is 90. We want to find the speed of gear B. We have this one, it's equal to the what? It's equal to the gear ratio. Remember, we talk about number of teeth of gear A over number of teeth of gear B, which is the gear ratio, and we found the time already is 1.5. You multiply and you get it very easily. It's a very straightforward calculation. Are you with me? Hello? Okay, good. Now, good. Now, if you look at the other way around, if I have my driver gear is now just now we see this one. Okay, this look at this picture. This is a smaller gear driving to a what? A bigger gear. Am I right? What if you have it the other way around? Your driver gear is a big gear, but your driven gear is a small gear like this. It's the same thing. It doesn't matter about the size. We do the same calculation now. We see that in gear A now the number of teeth is what? 40. It has more teeth. Okay, whereas the small one, the gear B is only 10. And you can see the way they rotate is always in the opposite direction. This one now is in what? Is in the anti-clockwise direction. Therefore, your gear B must be what? Rotating in the clockwise direction. You follow me? So far, so good. Okay, now, same thing, the gear ratio never changes. Always number of teeth of the driven gear divided by the number of teeth of the driver gear. We work it out. In this case, straightforward, you get 0.25. Okay, now look. Which one rotates faster? Is it the driven gear or the driver gear? Driven gear. Okay, so that one rotates faster. Now, how much faster? We're going to know that. Okay, now, if gear A rotates at the speed of 12 RPM, now, gear A is a big one, right? It's the driver gear. What is the rotating speed of gear B? What do you think? What should be this one here? How fast it should be going? How many times faster? 4 times faster. How do you get 4 times faster? Let me ask a question. How do you work it out? You got 12, right? 12 is what? 12 is the rotating speed of what? Gear A. Am I right? You divided by the what? The gear ratio, which is what? 12 divided by what? 0.25, and that is equal to 4. Am I right? Yeah. That's how you get 4. 48 rather, not 4. 4 times is 48. Am I right? 48. So that means the small gear rotate what? The speed is what? It's a 48 revolutions or rotations per minute, a lot faster. You follow me? So that's basically what it is. Okay, now you can try some of the things here. Now, what if you have 3 gears? Oh, now, that's how we're A and B. Now we got 3 gears, but let's say that this gear is what? Has 10 teeth. The middle one, the B gear, has 20 teeth, and the gear C has what? 15. Watch out very closely here. Now, we work at the same ratio as what we know, because this one will drive this one, right? This one will drive this one. So that this one will be the driven gear, this will be the what? Driving gear. But over here, this will be the driven gear, this will be the driving gear. You follow me? So that's how you will see it. So same thing, I work out the ratio as it is, as you can see here now. So I'm not going to go to the calculation here. You know how to calculate the gear ratio now. Now, if gear is a driving gear, what is the gear ratio of gear A to gear C? Oh, now I'm talking about these two dads. Now, you notice one thing. This gear does not interlock with gear C. Am I right? But it does move gear C. Why? Because it goes through the gear B. So there must be a way to calculate what is the gear ratio between what? A and C. Now, how do we do it? You watch out here very closely. That's how we do it. We first of all to find the gear ratio between gear A to gear C, you see what? We take the gear ratio of what? A to B times the gear ratio of what? B to C. And we've just done it. You see that? So you multiply the two together, these two ratios together, you get this one here. That will be the gear ratio of gear A to gear C. So you can go straight away to it as such. Follow me? Okay, now the thing is, what else do you observe in this calculation? Who can tell now? I want to observe now. I show you the gear ratio of gear A to gear B is gear ratio of gear A to B times this gear ratio of B to C. So we got fine, that's correct. But what else do you see in the above? Who can tell me? Can you find anything? No. What if I were to take A and C together? Now, suppose that gear A now is rotating at 100 RPM. We can calculate the gear B and C. See what happened now, okay? Now let's see, we calculate them very closely. Same thing, that's quite easy, right? So that's how we were to do it. Now, can we find the rotating speed of gear C in another way? Can we do it in another way? Let me ask this question. Can you look at the gear ratio of these two and you tell me what is the gear ratio of these two? What does it mean? Can you see that 15/10 is the same as what? Yes. Yes, right? You can take these two gears, A and C, ignoring the B. You still get what? 3/2 or 1.5. So that is one thing that you see, that this gear does not affect the gear ratio between A and C. In other words, so now I say, okay, I find a shortcut now in calculating the gear ratio of two gears which don't interact directly, but they interlock via a middle gear. You see that? Now if you see this way, then if I got more than 3 gears, let's say four gears, 1, 2, 4, and A is the driving gear. The last gear is, let's say it's a gear D. Can I find the gear ratio of gear A to gear D? Yes, you can find it also. That's the beauty of this kind of interlocking gear here. All right, so that's why I'm going to show you what you can do here. Now, before I go to the bicycle, can you complete question number 3 on page 2? These are all the calculations that you can see here then. 3 parts A, B, C. Come on now, you try it. A, B, and C. Any problem? I'm trying to see. You can discuss, yes.
Between B and C, do I start with B first or C?
What? Between what?
B and C.
B and C must be only these two. Forget about A. That means B and C.
I do 60/10.
No, which is the driver gear, which is the driven gear?
This is the driver gear, this is the driven
Okay, good. What's the gear ratio?
gear. 60.
It must be what? This over this, right? Yeah, okay, good. Okay. Any question? Feel free to raise your hand. I will address the questions if you have any question here. Yes. Sorry? Okay, no. I thought you had a question to ask me. Okay, you tell me the answer, okay, for the three parts. Anyone who's done, just tell me the answer, what that is. You have done it? Anyone have done it? Raise your hand. You have done it? Okay, part A, okay, do part A, 3A, okay. You come forward and show me how you do it. Come, don't be shy. Now, okay, see how she did the part A, okay? Now, okay, she want to do the part A. Now, I might give her a chance to do the part B and C later on, okay? Right, bigger, big, right, big, yeah. Okay, all agreed? You say the gear B will make what? 3 revolutions, am I right? All agreed? Okay, good, well done, yeah. Okay, very neat. Okay, who has done B? Come forward. Okay, what's the grade ratio between gear B and C? No, just do it, just carry out your B, yeah, your B part. Hmm? What A3? No, it's a 60 over what? It's a 60 over 60 over 20 is 3. What? That's great. Huh? Oh, no, just after lunch is then I will come later on. Later. No. It's okay. Okay. One over 6, right? 1 over 6 for B.
Wait, for A it says when gear A says makes one complete revolution.
Yeah, when A make one complete revolution, A make one complete revolution. How many that gear B makes? Okay. One A make one complete revolution. How many that gear B make? Okay, never mind. Just put it down first. Okay, let me finish up first. I'll go back to it. All right. Now, how about the last one? Who want to try the last one? Anybody? No taker for the last one. What is the gears? What's the gear? Okay, when the gear system is in motion, let me start moving. What is the rolling speed of gear C? Is the last one now. I give you the gear A, which is driving which is the driving gear, right, is 64 RPM. How to find the speed of the gear C? Doesn't matter what. Don't worry about right or wrong. Don't worry. Don't worry. But just never mind. You make a mistake. It's okay. Don't worry about making mistakes.
Yeah, the C.
Okay. Thank you. I don't know. I just put down first. Okay. Now let me go over all these three. Okay. No, don't worry about right or wrong. It's okay. Learning is about. Don't worry about making mistakes. I think in learning we make mistakes here and there. Fair enough. But these are not fatal mistakes. Don't worry. Okay. Yeah. Don't stick a finger in the electric socket there. That's a fatal mistake. This is not fatal. Okay. But if it's not fatal, I would say that what is a mistake? Mistakes provide what? Opportunities for learning. You learn something. Now look at the first one. Somebody says that what is the when gear A make one revolution? Look at A, one complete revolution. How many revolutions does gear B make? Now look at the picture. Well, look at the picture here. Okay, which gear is big? A or B? B. So when A make one round, you think that B will make 3 rounds? No, right? It's only a fraction of it. Am I right? Yes. It's only a fraction of it. Because what? Because that big one is what? It's a bigger, right? So of course, when you make one round, this guy is only making a what? So in that case, even though the gear ratio, yes, is what? 60/20. Am I right? Fair enough. The gear ratio, okay, the gear ratio in this case is 60 over what? Over 20, okay, which is equals to 3. You say that. Now, what is this meaning? When gear B, listen, make 1 rotations, gear A will make how many rotations? 3 rotations. But another question says that is it the other way, right? We say when A make what? 1 rotation. 1/3. In other words, a 1/3. So the answer is that. So the answer is what? Gear B makes what? 1/3 of a rotation. Am I right? Yes. Never mind. That's how you learn, as I say. Okay. So you must understand which one turn more. Look at the size. I give you the picture that you can see the size here. Okay, fine. Anyway, so in other words, we know that it must be 1/3. That's the answer. Okay. Yes, fair enough. Now look at the second one. What do we want? What is the gear ratio between gear B and C? That's quite straightforward because we know the driven gear is a gear C. The driver gear is a what? It's a gear B, right? We take the ratio there, we take 1/6. So that is correct. Yeah. Okay. So that's basically what we have here for. Now, how about the last part? Is this correct? Wrong. Wrong. Okay. Never mind. Why is wrong? Let's see now. How do we do it? We want to find what? We want to find the rotating speed of what? Gear C. And we are given the gear A. Now let's see. Gear A. Gear A, what's the speed? 64 RPM. Am I right? And we want to find the what? The speed of gear C. So we want to know the gear C. Gear C speed is equals to what? We don't know. Am I right? Question mark. Sorry, there's a question mark here. Question mark. What that is? We're going to find this one. How to find this one? Hello? How to find this one? No, to find B. He says, okay. You can find the gear ratio. That's right. You can find the gear ratio between what? A and C. Yeah. So now I'm talking about the gear ratio. Okay, see that? The gear ratio now. Okay, between A and C. This is A and C. Yeah? This is A to C. Okay, I'm talking about that. That's equals to what? Look at the picture here. Is what? A to C is what? 10 over 20. Am I right? It's what? 1/2. Am I right? Is it 120? No, is it half? Are you with me? Half of it. That's right. Actually, from here, you can see very well. If the gear ratio is half. Now, if I know that gear A, the speed is 64. Now, let me ask you this question. Which gear will rotate more? C. It must be faster, right? So therefore, the speed of, so that this one, the speed of C, gear C is what? Is 64. Now I can know that. Is 64 what? Divided by half. Am I right? Am I right? Not by half. 0.5. And that should be your answer, which is what? 128 RPM. Am I right? It's the same. So 1, 2 is correct. Am I right? So that's how you do it. Okay, anyway, so much for the gear. I think I will just now, okay. I don't want to do the last. Okay, I want to show you this picture here. Come on, listen. This is the picture. That's the last question here on the gear. I don't want you to do it. You can do it back home. I'll show you about the bicycle. So this picture here, here's a bicycle. Okay. Now, the bicycle, if you look at it, where you cycle, sorry, because there's a cover here, I cannot remove it. So I have to use this picture to show you. Do you see that this gear is bigger than this gear? Am I right? Yeah. Now, of course, there's a chain. Now, these two gears, they do not interlock directly, but they rotate via a chain. There's a bicycle chain here. Now, another thing, do you see that now, because they do not interlock directly, these two gears now will rotate the same direction. Am I right? Yeah. If this guy goes this way, the guy also go the same way, obviously. Unlike the interlocking gear, which they will rotate in opposite direction. Well, in this case, because of the chain, they all rotate in the same direction. And we call that the front gear. That's where you pedal your bicycle. And that's the rear gear. And you notice the rear gear is smaller than the what? No. Why must be the where you pedal is a bigger gear? Why the one at the back is a smaller gear? Why? We have just learned. Because if you were to pedal the big gear, one revolution, the small gear will have to go to many times. Am I right? More than one time. So meaning what? It'll be faster speed. So now you exert, when you step on it, the guy will move faster. That is important. So you must understand that. You can go faster because you step on it. If the gear is the other way around, I tell you what, you have to pedal very fast and the bicycle just move very slowly. Because the back gear is big driven, it just moves slowly. That's why now in bicycle, the way you pedal is always a big one, okay, a big gear. Now, but you are going to find another bike. This is a speed bike. Now, speed bike is a bit different. Speed bike, look at this picture here. It's not one gear. There are many gears here. We just real get many gears. We call the cassette. By the way, the cassette. Okay, the front gear is the same, but this one is a bit different. It looks like this. Do I have one here? I thought I have cassette here. I think there's a one here. That is a kind of a gear you're talking about for the spike, for this sport bicycle here. You want to pass it around? You look at it. Watch out, don't get cut. Sharp, yeah, watch out. Just hold it like that, okay? Now, why is like that? Because you can change gear here. That is why you see at the control there, right? So there are many, many gears here. So what they have is that they can change the gear if they, let's say, if they want to go uphill. Now, when you go uphill, you need to pedal a lot harder. Am I right? Take the bigger gear. You're right. Take the bigger gear. You got the bigger gear at the back give you more force. So smaller gear has smaller force. Bigger gear is a bigger force. So when you pedal on the smaller gear, driving the big gear, it will push you up. So that's why over here you see that this gear is a much bigger than this gear here. You follow me? So that is how they can manage in the sports bike here. You know, they got multiple gears. Usually, I think they're about 4 or 5, depending on the complexity of the of the gear system here. All right. Now, anyway, the last question here, I wouldn't want you to do it now. Never mind. Okay, I think some of you are kind of tired after the lunch, and I don't blame you. You want to have a game?
Yes.
Each one, take one. Pass around. No, you take this one. Each one, take one. Wake up. Take one string. Each one, take one string. Oh, and turn it together. Take one. Take one. Any extra? Pass back. Take one. Take one. Isn't take one. How many get there? Extra? Give back to me. You got one? Why you want so many more for what? You hang yourself, isn't it? Any more? Come take it. Pass around. Not enough, don't worry. I will give you. That's enough, much more than enough. Take it up for me. Take it up. Wait a minute. Any more? Oh, there's some more here. Take one. Yeah, might take. Anybody? Don't hang yourself, okay? Everybody got one? Okay, I'll tell you what to do. Come on. Now watch me very carefully. Can you all tie these knots like that? Just like that only. Oh, easy, right? Kid stuff. I can do it. Well said. Okay, easy, yeah? Now, I now want to tie the same knot again. This time round, maybe with one hand. You decide how you tie. Only either your left hand is okay, or your right hand, up to you. I don't care how you use it, but you tie with one hand only. Okay? One hand only, yeah? How do you do it? Somebody use teeth. Anybody can do it without the teeth? What is the year 2 plus? Okay, now you show me, come on. You show the whole the class. How to do it without the teeth, okay? Okay, so you do it without using the teeth. Now, do it one more time, okay? I'm thinking of it. Okay, now she do it. Watch out. Wow. Hey, no. No, you're just supposed to hold it. Oh, no, you're supposed to hold it. You hold it. Anybody have done it? Come on. You've done it? Never mind, it's okay. You've done it? Hello, friend, you've done it? You've done it? With one hand? Okay, she's done it with one hand. Show them how to do it with one hand. No, you hold it with one hand. No, you hold it with one hand. No. You hold one hand first. Let go. Tie the knot. Okay. Use the floor there. Okay, well done. Anybody else? Good. Well done. Okay. Not yet. Okay, you done it? You done those? Okay, come. How to do it? Come now. This guy will do it in a different way. Okay. You wait. Untie this off side here. Okay, go. Go ahead. That's okay. See how you do it.
It's a really flimsy process. I only got it at once.
Okay. Also, you just use a finger to touch it. Hey, don't hang him, please. Don't hang him, okay? Yeah. Okay. Now, listen. I want to tie the same knot again in a different way. This time around, I want you to make a loop on both ends on your hand and put it on the hand there, okay? A loop. You can be bigger, it's okay? Just a loop. Just make a loop here. Tie a loop at both ends. Wait a minute, tie a loop at both hands. Just a minute, let me make my loop first. Yeah, loop here, a loop like this on both ends, okay? Both ends, huh? Okay, may look at both hands. A bit, not both hands, both sides. Okay, listen, huh? Both sides, and make sure it's big enough for your hand to go in. Don't be too tight. You see, so you handcuff yourself with a loop. Your handcuff. Not in the head, as a hand, no head. Can you tie a loop? Okay. Okay, do it. Okay, give me a hand. Hey, don't tie on your hand. I say that. Come on, do properly. Don't tie on this one. Now, have you made a loop? Come on, make a loop first. Come on. Don't put a head. Come on, take it out. Okay. Now listen. I want how to make. You make a loop. You know how to make a loop. Just now I'm doing it. Just make a loop. Okay. Now. Remember just now you tie this knot, right? Remember about this knot? Just now when you tie this knot, right? Remember about this knot that you tie? Okay, remember this knot, right? You tie? Now, the only requirement is that I want to tie the same knot like this. Okay? Listen very closely. Without removing the two ends, The ring's there. That's it. Make sure that you don't take it out. So can you tie this knot without removing the ring from the both hands? Think about it. How to tie these knots without removing from your hand. Okay? Now you think how to do it. Come on, you do it. Anyone have done it? Raise your hand. Then you can demonstrate to the class. You tie this knot? Huh? You tie? No. What do you mean? Wait. Don't you tighten it? I mean, just tie it only. You tie already, isn't it? Okay, you done it. Good. It's just done it. Yeah. Okay. Wait. Okay. Just untie it. Yeah, Sarah. That's Sarah. Anyone have done it? You done it? I don't know whether done it. No, you haven't tied any knots yet. I haven't seen any knots. Okay? Okay, now. This girl have done it, okay? Can you demonstrate to the whole group here? Slow motion. I don't see the knot here. The knot must be in the middle. The knot must be, no. Where's the knot? That's what I showed the knot, remember? No, you come forward and show. I want you to tie this knot, listen very closely. This knot here, not by the side, but this, sorry. I want you to show you that this knot here. Like this, the knot must be in the middle, okay? You see that? It's a simple cross knot here, that's all. Very simple. Can you tie it?
I can't open it up.
No, you go to the side already. You know, it should be right in the middle. You see, it should be like that. It should be like that. You see, very nice one. You managed to do it.
I forgot how I did it.
You forgot. Try again. Huh? Looks like you have made. How come you make so tight? You see, it's a very loose one. It's a very loose one. You see, it's a very loose one. Make it loose one. It's not the tight. It's a very loose one. You can see that it's a very. You do it. I can't see. Right? How come it's so tight? I mean, why it's tight? It's off. You go. I think you go many rounds, isn't it? No. Not like that. No, not. It's exactly a very simple. Not just cross like that only. No, you cannot. I mean, I don't know how you do it, but you cannot have too many loops in the meantime. You try and see. You do it. I don't see the knots anywhere. I don't want to show me the knots. You are right. You are right. Yes. See. Wait. Yours it's too complicated. Sorry. How can be so many? No, it's not. It's not true. You see, I can untie it. Huh? How do what?
I actually try to tie it together.
Oh, yours. I tell you what. Maybe I give you another. Any extra string here? Is that extra string?
Yes.
Okay, give one now. You can tie again to put with this one. You don't want? You find another one. You do it? No. That's too complicated. Like, remember, it's a very simple knot. It's a simple knot. The knot right? You want to tie the knot right? See how I do it? Done. That's all. You let the knot go through your hand, not the hand go through the knot. Think about that. Reverse the process. One more time. It was like that, right? You want a knot here, right? You let the knot go through your hand. Right here. The knot go through your hand and not the hand go through the knot. Reverse thinking. Manage to do it? Sorry? Oh, near the camera. Yeah, what to say? No, what should I do? I just repeat my word. Okay, you want to tie these knots here without removing your handcuff. Okay, the ring is still on your both hands. As I said, you let the knot, you let the loop go through your hands, not your hand through the loop. The loop go through your hand. This is my hand. I let it go through. My handcuff is still there. And I let go, and here's my knot. And if you can tie the knot in this way, same way, you can also untie it. If you want to untie, you can try to untie it. Huh? Sure, go ahead, go ahead. Yeah. Okay, got it? Now, okay, wait, one more time. Come on, I do it in the slow motion, okay? Watch out, huh? Now, follow me. You make a loop. You let the loop go through your hand. Go over your hand. Let it come out. The loop come out, not a handcuff, never. You tied it. Are you with me? See? That's all? Cannot see? Okay. Okay, I will be nearer to this side. Okay, now you watch out very closely. One more time. The loop, right? See that? You make a loop, you tie the knots, okay? You let it go through your hand. Watch out my hand. You go through it, and I go through my hand. That's it.
It's attached to the table already.
Oh, sorry. Then you stay here for the rest of the day. You got it? You got it, isn't it? Come to the. Come, don't be shy. Right, you're good. Have you done yours? Anybody have done it? Come on. You've done it. Come on, show me. You've done it. Come forward. Come on. Don't be shy. Please. It's a very easy game, this one. You managed to do it? I show you one way. Okay, don't. Okay, then please don't. What do you want? No, show. I'll go toilet. Go ahead. Okay, you go toilet. All right, never mind. You can look at it how later on. Okay, let me move on to another thing then. Because I'm supposed to finish before you can go home. All right. So don't worry, I will give you early dismissal later on if I finish early. Now let's move on then. Okay, I tell you what, because I think the time is very pressing, I will, in the meantime, give a skip to the area of the rate of change first. If I have time, I'll come back to it later on, okay? If not, then I will leave this out. But I will go on to the area of polygon and the origami. Origami is very much of a hands-on later on then for the origami. Now, let me go to the area of the polygon. You all have learned polygon, by the way? Yes? What grade? Grade? Is it grade 7? Polygons. Grade 7, huh? You learn polygon. Good. So you're familiar with the grade. Okay. Now let's look at it. Now, I give you this handout here. Polygons. Come on, take some. Yeah, pass around. Anyway. Pass around, come on. Pass around. And extra, pass it back. Come on, pass around. And extra, pass it back. Pass around, please. And extra. Pass around. Say if extra, pass back to me. They have to pass back to me. If extra, pass to the back. Where the back hasn't got any. Okay. Now, listen closely. You learn polygons in grade 7. I think you also know how to find the area of polygon. Now look at this picture here. Can you find the area of this polygon? Assuming that these all are unit square, 1 cm, 1 cm. Okay, they're all square, 1 cm. Can you find this area here? What's the area of this polygon? How do you find it? Tell me. I don't answer. How do you find it? You count the boxes inside. But the trouble is that this one is not the whole box, right? So how do you add up all this little area, which is not the whole box? Not the whole square. Okay, how would you find it now? Let's say if this question I ask you, can you find this area here of this polygon? What strategy do you use? Do you find directly? Do you dissect this one into what? Triangles, a parallelogram or anything to find it? Can you do it? Now, if you were to divide it into which way? This way. With a triangle, if I do this way, then with a triangle, right? But can you find the area of this triangle? You cannot. Am I right? You know how to find the triangle, the area of the triangle, because you don't know what's the length, or what's the base, and what's the height. But you can find still. Now, you must look at this question in a different way. Do you see that this polygon is actually sitting inside a rectangle? Yes. Do you see that this polygon is actually sitting, you see the rectangle here? Am I right? Ah. Now, it's right inside the rectangle. So therefore, you don't know how to find the area of rectangle. Fair enough? Length times width. Now, of course, then you know that the area of polygon must be what? Smaller. How much smaller? That means you must take away what? All these areas. Am I right? All right, this outside. Then you can find it. So therefore, all I need to do is to find the area of the big rectangle. Then what? I take away the area of the outside rectangle. But what's outside? Do you see what is this rectangle here? It's a right angle triangle. Am I right? And that's easy. I know this is what? How many cm here? 3. This is what? I can find this area. Am I right? Can you now? Same thing here too. See, there are many, many. So you find all those things here. Then this is a 1, right? This is all square by itself. So you can just deduct all of them. How about this one here? What's the base for this triangle? The base is what? 1, 2, 3, 4, 5. And what's the height? 1. Now you have found all the areas outside that polygon, right? You find the difference, you get the what? You get the area of polygon. Am I right to say that area of the rectangle minus all those little triangles, whatever that is outside, you get the area of the polygon. Am I right? Yes. Please do the first part. This is the question what you have. Okay, can you please do it? Tell me what's the answer. Now find all the little region outside. Then you take the difference. No, thank you.
Good.
So who can tell me what's the area of the polygon? Come on, quickly. Use a calculator to do it. What? 24, isn't it, or what? Okay, then take away all the small little one. Yes, okay, good. That's correct. That's fair enough. Can take away, let's find little one and then take away all this, correct. Anybody got it? Come on. What's the answer? Yeah. What's the answer? Just tell me. What's the area? Find the area of the polygon.
This one also find area.
Yeah, of course, you take away all the little ones, right? Take all the little triangles. You got it? What's the answer? 14.5. Okay, I don't know what's the right. Okay, 14.5. Okay, somebody says that this area is a 14.5. I don't know whether all you have the same answer. I have no answer with me, but 14.5 cm squared. Is it correct? I don't know. What do you have? 17.5. Oh, I got 2 answers. Another person say that it's 17.5 cm. I don't know. Okay, there are many answers here. How about you? You got any answers? Haven't got an answer. 15 only. 15. Okay, I got 15.
Oh.
How come I got so many answers? That's interesting. Okay.
16.
Sir? Anybody have a different answer? 16. 16.5. 16, 16.5. There's so many different answers. Interesting.
17.
Are you sure? Don't anyhow shout, but
17.
sure 17. You got 17.
14, 14, 14.
No, not guessing. You must work it out. I'm going to guess. Huh? 15. 15 is here. What? 15.5. And now 15.5. Well, that's quite interesting. Okay, never mind. Don't worry about right or wrong. First of all, let's look at what it's supposed to be. Now, first of all, let's find the area of the what of the rectangle. Am I right? So, area of the rectangle. Hello, is equals to what? Tell me. 6 times 4. Am I right? Okay, good. 6 times 4. I got 24 cm squared. Okay, now I take all the little. This triangle is what? 1, 2, 3, 4, 5, right? So it's what?
Times 5.
Area outside the polygon is equal to what? It's what? It's a 1 over 5 divided by 2. Am I right? It's 110. Am I right? 110. So this side is 110. Am I right? This side is 110. How about this one? This is 1/3. Am I right? 1/3 divided by half is what? By 2 is 1 over 6. Am I right? Is it 1 over 6? Then I got this little one here, which is 1 square. Am I right? Outside. So this plus 1. I find all the area outside. I add up total area, the total area of all this. How about this one here? This is what? No, 1. It's not. Triangle is what? This is what? 1/4. Am I right? 1/4? 1/4. Okay. And last but not least, how about this one? The last one. 1 over 6. Am I right? Am I right? Now, how many areas do I have? I have what? 1, 2, 3, 4, 5, 6. I got 6 there. 1, 2, 3, 4, 5. I missed out 1. Is it? Do I miss out 1? Just now I start with which one? Oh, I missed out this one here. Am I right? Yeah. Top 1. So it's another what? 1 over 6. Am I right? Yeah. Now, who can tell me quickly your calculator? What's the answer for this one? Please tell me the answer. Use a calculator. What's that? 1 point what? 1.85. 1.5.
85.
Am I right?
Yes.
So these are all the areas outside the polygons. Am I right to say that?
Yes.
So therefore, what's the area of the polygon now? Now I can find the area of polygon is what? Must be equals to what? 24. Am I right? Minus 1.85. Am I right to say that? Am I right? Am I right? So that's the answer. You see, is this correct in the first place? I want to know. That's why I keep asking, is this correct? Is it 1.85 or 18.5? You tell me.
What?
Wow.
If all this add together.
I don't think that's. If you see the 6 by 4 grid, you can tell there's at least three squares of area.
No, I'm asking that how many areas you have this one, right? You have this one. 1, 2, 3, 4, 5, 6. Unless you want to take this as a what? Okay, yeah, show me. Okay, but you can write on it. Tell me.
But this part is half of this 1 by 3, so it's 1.5, right?
Yeah, this part is 3 by 1. No, I'm talking. Are you talking about? Sorry, I'm talking about this outside the triangle.
Yes.
Is a 3 times 1 divided by 2, which is 1/6. Am I right?
No, it's 1.5.
Oh. Oh yeah, correct. Okay, yes. Okay. So there's a 1.5. That means this one is what? Who can tell me what's the answer? No, the first one. Is it 1/10? No. Okay. Tell me. Yeah. 3.5. Okay. Second one?
2.5.
2.5. That's what I say. Ask what's the answer. Okay. What's the next one?
1.5.
1.5. This is a 1, right? This is also 1. And this one? 1.5, 1.5. Am I right? Answer? Tell me. All agree? Answer?
15. 15.
Agree? Yes. Okay, well done. Now, so you really have to go a bit indirect, right? To find the rectangle, then take away all those outside the region there, to find the area of the polygons. Now, listen. Now I put it onto on the lattice. This is a lattice plane. You see, that means what? It's a square grid. Now I put the same thing over here. For example, I'll just put it here like this, and you can see that it will touch many of what we call, these are the what? These are the points. This is a vertex, this is a vertex, right? So there are many points here. These are inside point. We call the interior point. These are interior point. These are what we call the green. We call the boundary point. There is a boundary of that quadrilateral. You follow me? Now, what I'm going to say is that I'm going to use the points to find the area of this polygon, or rather, this is a quadrilateral here. How can I do it? Well, there's a very nice little theorem that it's called the Pick's theorem. And that's what it says. The theorem says that if you are given such a polygon, like what you see here, in this case, a quadrilateral, the area of the polygon is given by this formula here. Now, look very closely. In this picture here, you got the boundary points, you got the interior points. Interior points are the point inside the polygon. I is the number of interior points. B is the number of boundary points. And what it says that if you take the sum of the interior point plus half of the sum of the boundary point minus 1, you shall find the area of the polygon. It's a lot easier. Am I right? If I put it onto the lattice plane here, with all the points that you see here, I can find the area very fast. I don't have to worry about looking at the big one, you know, the big rectangle, take away all the small little one here before I can find the area of the quadrilateral here. Now let's see how to use it. Okay, I take the same example here now. I got this 3 region. Okay, now if you do it in the old way, what do? Just now you have done it in this way, am I right? This is the old way of doing things there. Now, what if I were to use the so-called this lattice points here? Now, this is a formula I have. Now, see what I'm doing now then. You see that the interior points, how many? 1, 2, 3, 4, 5, 6, 7. So I is 7. How about the boundary points? Now you count the boundary points. You must count all as long as it passes through those intersecting points. You count them. Okay, so count them. How many of them? 8 of them. So all it says that the area of a quadrilateral is equal to 7 plus half of the boundary points minus 1. And you work it out, it's the same answer as what you would do it by the traditional method. That is the Pick's theorem way of doing it. It's a lot faster. It's a lot faster. Okay, now, with that, now can you find this area? Just like you say, it's 15, right? Same one, huh? Remember? Now you use the Pick's theorem to find this area. Come on. You count the number of interior points, the number of boundary points, and see whether you get the area of the polygon to be 15. Come on, you try it now. You try it. Same one. Now you do it in a deep time. Now use the Pick's theorem to do it. You got the same answer? 15, right? Ah, so it's the same as what you got earlier on, remember? And so now you find another way of doing it.
So what's the formula?
I is the number of interior points. Now, the only thing you have to watch out for is this. All the vertices, the coordinate must be integers. It must be, it cannot be fraction or anything. It must be integers. If the coordinate is somewhere around here, of the vertex, you cannot use the Pick's theorem. It only works with integer vertices. Follow me? So that's basically what you have to watch out for. Now, once you know it, You can do exercise now. The next page, there are all kinds of shapes. Come on, next page. You can try them out. This is the number of boundary points. Boundary now. No. This is the boundary. This is the boundary point. This is the point, right? These are the boundary points. You see that? 1, 2, 3, 4, 5, 6. This is a hexagon, right? Hexagon has 6 boundary points. Okay.
It's on. The line is going for like this. Count as boundary line. Boundary points.
Yeah. As the boundary, these are all boundary points. Yes, correct. They're all boundary points. Yeah. These are the interior. Yes, correct. Yeah. Okay. Now you can do the next question here. Come on. You got it?
Nice.
Is it easy to find now?
Super easy.
Super easy. Okay.
Answer nine.
Make sure you open it's the same answer, isn't it? Okay, that's good. Now try the second one anyway.
Yeah. One.
Some say 9. I don't know why. Got 8 or 9. I don't know. You count how many. You make sure it's correct. How many points you have here? Your boundary points. How many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yeah, you have to count. Okay, so be careful. Yes. Supposed to be 9. Yeah. Supposed to be 9. Now the last part here. Let me see. The last part, you're supposed to create your own polygon and find the area. Come on, you can create any shape that you want. The last one, let me see. The last one here, it says as well. You create your own polygonal any work that you want to create, okay? On the square grid. Take the square grid. You have a square grid paper, the earlier one. You draw any shape that you want. Okay? Then you find the area of your polygon. Fair enough. Assuming that the length is always 1 cm. Take your square grid there and then create your own polygonal work. Anything you want to draw. You got 9. This one got what? 17, isn't it? This is 17. Is 17 the second one? 18. Wait, I don't. 18. Okay, count again. Okay. I don't know who's right, who's wrong, but we count again. Yeah, create your own shape and then calculate the area of your polygon you have created. Come on, you can create one. You can create any shape. Or you haven't done this one yet, okay? So you can do it first. You create a shape and then you can just calculate the one that you have done. Now see, okay, whether you can calculate it. Any shape. You managed to do the first one, okay? You managed the second one. We'll try it. Come on, try and see. But question, tired? What happened to that? Don't tie her hair, like, goodness sake. Tie her hair. When is the fire here? Why cannot? Why? You can count the points. Count the points, come on. Boundary points and the interior points. Just count them. That's easy. Just counting points, right? You know how to count. You can count what? These are the 1, 2, 3, 4, 5, 6. Just count them, that's it. You want B is the number of boundary points. Inside got how many? You only say very few, it's like 1, 2, 3, only 3 points only. That's it. So interior points only 3, right? Boundary has more, fair now. So yeah, just count the outside one, you know. Yeah, so these are the, yeah. So this I is equal to 3. Then you find the B. B is the boundary point. So how many you count? 1. No, this one is not. This one is not, no point here, right? It's this one to this one. That's all, huh? Okay. 14, huh? I don't know how many. 14, isn't it? Okay. Make sure it's correct. That's all. 14, okay. Now use the formula to do it. So I plus B over 2 minus 1. That's it. All right. Can you? 19, huh? Okay. So it's 19. Am I right? It's 19. Okay. You got it? What is it? What's the area here? You found it? You found it? You can count the dots here. How many dots? The boundary point is to count all these dots here outside. Okay. Here you see the interior point only 3, right? 1, 2, 3. That's only 3 points. So I is equal to what? 3. When I is equal to 3. Right? I is equal to 3. Yeah. Okay. Then the B. Now B is the boundary point. B is equal to the count. B is equal to count how many? Okay. 1, 2, 3. Count outside. Just point 1. Go down. No. 1, 2, 3, 4. That's what? 5, 6. Go all the way down. 7, 8. Go further. Go further. 11, 12, 13, 14. 14. All right. Then use the formula. I plus what? B over 2 minus 1. That's the answer. Easy. All right, easy. That's it. Okay, hello. Getting a bit restless now. Let's sit down. Come on, sit down for a while. I'll let you go. Don't worry. You'll go earlier. Have you found the answers? The first one is a 9. Am I right? 9 cm squared. Second one is what? Second one, 19. Okay. Yeah. As I said, you can create your own polynomial, shape anything on the dot paper there and find the area by yourself later on. No, they say what's the first one is what? 9. It's 8.5 or 9, the first one. 8.5. 8.5, isn't it? Hello? 8.5, sorry, 8.5, not 9. They told me it's 9 just now. Okay. 8.5. Okay, 8.5, correct? How come they say 18.5 for second one? Okay, hello. Second is 18.5 or 19? How come got 2 different answers? Now tell me. Just count the points. Let's see. How many interior points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Am I right? Interior points, 15. Interior points. How about boundary points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it 10? 10, huh? So boundary point is 10. So it's what? So 10 is what? It's a boundary point, right? Interior points, that's what we say. How many interior points? Don't worry about that. That's one. So how many interior, come on, how many interior points? That's what we say. 15. So 15 plus what? B is the, how many B here? 15 plus what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 over 2. Hello? 10 over 2, am I right? 5 minus 1. 19. So it's 19. Whole number. Okay. Whole number. Now, let's do the last one now, okay? I think you're getting a bit restless now. Let me go to the last one. Let's do origami now. This one you'll get it, okay? Come on, sit down. Let's do origami now. Okay, sit down, please. Quiet. Now this one, I think I want you to do some work, okay, for the origami. You know what's origami? Yes. You see, origami can make lots of things here. It's a very old art form, by the way, okay? Started in Japan. This word origami basically is a Japanese word. The word say ori means what? It's a folding, and kami is paper, so it's a folding paper. That's the meaning of origami. In the good old days, basically it's used for decoration or for any ceremony whatsoever there, okay? But now it becomes a form of art. People, just enjoy doing the paper folding. You can see that you can fold this, this is what you call this, a ninja star. You know, the ninja, the star, the flying star, right? And this is the butterfly. So you can fold all kinds of things here. But today, of course, we won't fold all the things here, fair enough. But today, I want you to now. You see, this is a more complicated thing. You can fold an elephant or even a dinosaur, the T-Rex, for that very matter. All right. But today, origami has many practical applications. It can be used in engineering, in medicine, in architectural design, so on and so forth. Okay, even you can go to the space exploration for that very matter. So I think that it's good to, learning origami have to develop patience, precision, and creativity. You create all kinds of things here. I will show you what it means to create all kinds of things here. All right. The thing is, it's quite simple. It's only a piece of paper, a simple sheet of paper, and you create all kinds of things here. That's the whole idea about origami. Now, today, I want you to create this Japanese crane. Every Japanese student visiting in Japan will learn how to fold this crane. You know how to fold this crane? No. Okay, never mind. Then you have the rest, okay? Those who know how to fold it can have the rest. Okay, don't worry. I got all the organic paper here of different sort of color, okay? You can decide what you want, and I'll pass around. Maybe at the back. Wait, tell me to pass around at the back. Just a minute, to pass around. Now, don't waste it, okay? This one, take one sheet. If you want to take two, I think should be enough. You can take two if you want to, okay? You choose a color. I don't know now. Okay, different colors. You want to get different colors? No? Huh? Choose color. Okay, let me take out all the colors. Wait, let the pass to other people. Come on. Take some, pass around. Whatever color you can take. Come on. What color you want? Yellow, green. Okay. Can you have what? Pink color. Just a minute. Wow, what's this color? A pink color. Take one. Take one. Okay. Take one. Okay, everybody got one sheet. You take what? Another pink color. Okay, you have any color? No, don't fold, please. Don't fold yet. Okay, all of you have a one. You have one? You have one. What color you want?
What color you want?
Red, no more. Okay, one more. Red. What do you want? Blue. Okay. Huh? Pink color. Pink. Yellow.
Oh yeah, I saw purple.
No, yellow.
This is
Yellow, is it? What do you want? You tell me.
sorry. I'm so sorry for being so picky. Wow.
Orange.
Oh, orange yellow.
Orange. Okay.
I'm so sorry.
What do you want? Okay. Okay, good. Put it back. Okay, all got the papers? No. Okay, now come on, listen. I will show you how to fold this crane. Okay. So this is the end result. Hello. Okay. This one I just folded it. You can see that. I want you to do something like this. Okay, so that's how it looks like. Now, how to do it? Okay, now watch this video very carefully. I will stop, okay, for you to fold. Now listen, this is step by step how to do it. Watch quiet, listen.
For the origami crane, we use a square sheet of paper. Any kind of paper will do the job. First, fold the paper in half, both ways, as also shown in the picture on the right. So now we have made 2 belly folds by turning that.
Okay, I stop. You know the fold it? The first way is this, right? You fold it. After that, you fold the other way. Fair enough? You fold this way. Okay, you open up, you fold this way. Fair enough? Then you open up, you get a cross, am I right? Yeah, okay. This is the first 2 steps. Now, watch out, okay, now I will go on, See what I do now? Listen now, watch closely.
Are now mountain folds, and we fold the other way around diagonally both ways. So first in the one direction and then in the other.
Okay? So you open up, then you fold it this way. See that? You fold it this way. Okay? So you fold it. Okay, all done? Okay, now listen, this step 3 and 4. Now let's go further. Now, watch out very closely here.
Okay, now turn the sheet so the yellow creases are mountain creases and push in the center and collapse like so. Make sure that the open creases and push in the center and collapse like
Push to the
so.
center and collapse. Collapse it. Push to the center and collapse it. That's what they want. Yep. Something like that. Yes. Okay. Yeah. You push it to the center and collapse it. Okay. One more time now. One more time. Now watch out very closely. Yeah. Okay. I rewind. Okay. That's this part.
Okay, now turn the sheet so the yellow creases are mountain creases.
They call it mountain crease. Okay, this is a mountain crease. Okay, you must top of the mountain crease. Okay, you don't do it, do it this way. Now mountain crease is here. Okay, now see how we fold it.
And push in the center and
Push to the
collapse
center.
like so.
Okay, push to the center.
Make sure that the open part points towards us. Take one of the flaps and fold it along to the center line. The
Yes.
edge align with the center crease. Exactly. Make sure that the open part points towards us.
Okay, wait a minute. You meant to fold up to this stage first? No, like that. It must be like that. You see that? Okay. Yes. There must be a pocket. Am I right? Good. That's correct. That's correct. Good. It must be like that. Correct. All of you got the same? Oh, you got it. You see, she got it very fast. This girl. She got it with me, see? Yeah, good. Okay, never mind. Don't worry. It's all right. Now, let's, okay. Once you got this stage, now let's see how to do it. Watch out.
Make sure that the open part points
Now, watch
towards
out,
us. Take one of the flaps and fold it along to the center line. The edge align.
Okay, watch out. It's the one that's open. You fold this one. Make sure you move. No, that's not right. You fold this. Ah, correct. That's correct. Okay, correct. Yeah. Let me see whether fold it this way. No, let me see whether. No. I think you fold it in the wrong way. You fold it. It should be this way. This way. This way. This way. Then okay. You fold it this way. Correct. Okay, you fold the right way. Correct. That's the right way. Okay. You do it on both sides. Same the other way. You do it on both sides. Okay. Once you fold it this way, make sure the side is open. You want.
With the center crease. Exactly. With the flap on the other side too. Then we have a kite shape and fold the upper part of the kite back.
Then turn it back. Okay, then turn it back. Yeah. Okay, turn it back.
Make sure not to go too far. Just align with the edge. Now open it up again. What we'll now do is called a petal fold. For that, we lift the upper layer and
Okay,
crease
replay. Replay. Okay, replay.
with the
Watch out.
okay. Make sure that the open part points towards us. Take one of the flaps and fold it along to the center line. The edge align with the center crease. Exactly. With the flap on the other side too.
Okay, you get to this point, up to this point. Which way you are doing? You're right. Yeah, it's okay, don't worry about it. So you must make sure to get to what he's showing you up to this point first, okay? You're correct up to this point, no problem. Okay, now let's go on. And we got up to this point. By the way, those who have done it, please help your friend who hasn't got it. Okay, help one another. Now let me go on, okay? You help one another here. Please help people. Oh, sorry.
Make sure that the open part points towards us. Take one of the flaps and fold it along to the center line. The edge align with the center crease. Exactly. And then with the flap on the other side too. Then we have a kite shape and fold the upper part of the kite
Okay,
back.
Okay, flip it back. Okay, that's it. Yeah, turn around and turn it the other way around. Okay, correct. Got it this way? Up to here. Okay, good. Watch out.
Make sure not to go too far. Just align with the edge.
Now watch out, huh?
Now
He open up.
again.
He open up. Now watch out.
It's called a pedal fold. For that,
Ah, that's it.
first,
Open up. Okay.
the upper layer.
Okay, that's it. Open up. Go back. Okay. Ah, correct. So open up. Okay, open up. And once open, it should be like that. No, okay.
And crease. The crease is here.
Ah.
So we get a leak.
Okay, like that. Okay, sorry. My mistake.
Repeat that so you can see better. Paper moves like this.
Okay, you got this up to this point? Good. Now let them go on. Okay, let me go on then. Okay, turn around.
Pedal fold on the other side. So first we make the diagonal creases.
Same thing.
Pre-creases.
The other side now. It's the same thing. You just do on both sides, it's the same.
The first layer.
It's the same as what you did earlier on. It's the same process.
Flatten the shape.
It's the same process, by the way, friend. It's the same process.
So you just have to reverse those two creases, this one and the right one here. That one.
Yes.
Exactly, like so.
You should get a diamond shape. It's a diamond shape at the end of the day, the diamond shape. Just open, right? You flip over here. Okay. Then it's the same thing that you do. You do it again. One more time. One more time. You do it one more time. Okay, turn it this way. My goodness, I just have to make a plane. Correct? Okay, good. Yes.
I don't know. The video was going too fast. I don't know what to do after this.
No, then turn around. No, wait. Open up. You see, that is basically what you're saying. You turn back. You do the same thing again over here. Same thing. Like what you do on the other side. Then you again open it up. Okay. It should form this little diamond, the diamond shape there. You got a diamond shape there. Oh, you got the diamond shape. You got the diamond. No, you haven't got the diamond. No, this is not what I think you fold it wrong. Never mind, I will show you later on, okay? Never mind. You can see what you've done. Why do you show him how to do it? Come on. You show him how to do it. Show him how to do it. Okay? You show him how to do it. Okay. Now listen. Okay? I carry on. Once you got a diamond shape, now that's what you do.
Okay, that's now a bird base.
You see that there's a diamond?
Called. And we'll take the
now watch out this time.
This one, and fold the edge nearly to the center. Not all the way, just nearly. That will make the inside reverse
Okay,
folds
watch
will
out.
make later on easier.
You flip this one. You see what's how to flip?
And also the flap on the other side.
Yes. Now you flip another flip. Second row.
Also, both flaps on the back. Oh,
Okay. You fold one more time. You fold one more time. Correct. So you have to fold one more. How come you fold one more time? That's what they want to fold. So one more time like this. Fold it up. Both sides. Both sides. Fold it one more time. Correct. Yes. Fold it one more time. Both sides. One more time. Okay. Fold it one. You fold it one more time like this. Correct. Just fold it. Then the other way.
Yes, sir. Yes, sir.
Yeah. Yeah. Okay. All right. Let me go on.
we fold it in half, so turn your sheet and repeat. Again, remember not to go all the way, just nearly to the center. Okay.
Okay, now you got this way up to here. Both sides the same. The same. See, you must get to this shape. Right? So that's what it is. Basically, these two, what you see here is the wing. Reserve these two for the it is for the wing. Yeah. Yeah.
I got it.
Okay. All right, let me go on. Come on. Listen. Now watch out, eh? Okay, now you see what?
One of them up is a pre-crease for the inside reverse fold. Now see that belly fold,
Oh, my God.
that will be now a mountain fold and
Make it louder, please.
reversed
Reverse it,
inside
push it
into
inside, push it
the
inside.
shape of the rest of the model. That's why it has its name.
Okay, I
So-
go back again.
Pre-crease for the inside reverse fold.
Pre-crease
Now
it,
see that
pre-crease it, say pre-crease. Wait.
Repeat the video.
Now watch out here.
Now we have those two flaps here.
Oh.
You see?
Pre-crease it,
One of
pre-crease it.
them up
Just turn it.
is a pre-crease for the inside reverse fold. Now see that belly fold, that will be now a mountain fold and reversed inside into the shape of the rest of the model. That's why it has its name. So reverse that fold like so, and
Okay, reverse it as such. Okay, good. I think you got it already. Yes, correct. You got it right. No. What is this one? Crease it nicely in the middle. Just crease it nicely. Okay.
I pre-crease maybe right like this, right? Finish.
No. You open it up, then you have to open up the scissor. Ah,
Oh, this is not rocket science.
okay, good. You got it. You also got it. You got it. Okay, somebody has got something. Yeah. So what you do is that. How come yours is like that one? This
Oh,
way.
wrong way,
I don't know whether the right or the wrong way. Yours is like the wrong. Right? It can. Rightfully, it should be the other way. I suppose so. You took the wrong way, most likely. Anybody got it? Okay, you got it. Yeah, you got one of it. Okay, so now that finish up the whole. Let's look at the rest of the thing here. Come on, you're almost there. Some of you is almost there. Come on now, watch out.
put the flap inside the model.
Now
Just
same for
like
the other
that.
end.
And repeat that with the other
Repeat the same thing.
the two flaps. You can do that in one step, like I'm showing right
Same
now.
thing. Okay,
or
we'll do on the
like with
one
the
side. Do on
first
the same
flap.
on the other side.
Okay. So now you have this shape. Fold down both of the wings, or make the wings by folding down
Okay, something
those
like
two
that.
flaps.
Hello. Usually get something like this. something like this. Well, this looks like it anyway. Something like this. Okay, you got it? Good. You got it, yes. You got it? I don't know, get it this way. No. I think that you did fold properly. Okay, you will show him how to do it. You will show him?
No. After this, then what?
Then in that case, you can make what the head,
Oh, this is the head, this is the tail.
the tail, and this is the wing, like that.
Wow, boss, alright, boss, for here, boss.
Hey, why do you show other people? Come on, you show her how to do it later. Yeah. Anybody show her how to do it? No, you show her how to do it. Come on. You do it? Yeah. Yeah, you're almost there. You're there already. In fact, it's good. That's
You sped through everything so fast that I
Huh?
didn't have a time to catch up at all.
oh. I think you fold it the wrong way. I think it should be this way. You fold the wrong side, just not this one. You fold the wrong side. Okay. And then you're supposed to bend a bit here. A bit here. Then what you do is that you push it up. Like that. Then you hold it down. This will be like this. You see that? You're almost there already. You do the same thing for this side. You again, do it this way. You bend it first, you open it up, then you push it up again. Same as what you do on the other side, yes. You're there already. Okay? Because you have done so many already. See? You make so many cranes. What happened to you? Okay. Hello, are you okay? No. Is yours in this one? Good. Okay, maybe just now.
Choose one of the necks to make it
One of them is the
neck
head.
and tail. I will take this one and make another inside reverse fold. And we're
Okay.
already done with our nice crane. Thanks a lot for watching. Let me know whether
That's
the
it.
diagrams on the right were useful or not. Bye.
Sit down. Okay. All right. Anyway, you can go back slowly. If you want some more paper, I got some more paper here. You can get some paper if you want to, and then go back home. You can slowly see how to do it. Okay, never mind. I'll give you some more. Anybody want some paper? Yeah. Some paper.
Hey, what a nail leh?
No, which one you want? Take a seat. You want a green or what color you want? Take one. Anybody want some paper?
You like green?
Give a green. Want any more paper? Anyone want some paper? What do you want?
I'm pink. Like this, like this.
Okay, what do you want?
I got two.
Take one. Take it.
This two.
Okay, take it. It's okay. No, give it to me, okay?
Oh, yeah. What you want?
Okay, you know.
Thank you.
Okay, take that. Okay. Anyone some more paper? Free paper, don't worry. Okay, let's sit down, come on. Now, don't worry. Anyway, if you don't get it right, don't worry. The first time you're doing it, sit down, please. All sit down, please. I think many of them have done it. And by the way, you can go to YouTube. There are lots of different origami shapes that you can fold. There are many other shapes, okay? But I'm going to show you a video. Some of the origami shapes are very complex and really very creative. How people do it. And do you know what? people who follow the complicated origami actually using mathematics. Serious. Math come into the artwork of origami. Now let's see what people are doing, okay? Let's see it. Now this is basically some of the steps altogether, 16 steps that just like you've gone through. These are 16 steps that eventually you will get the crane here. As such, these are the 16 steps that you have. Now, I would like you to watch this video here. Now, what this means, listen, this video will show you how far people have gone using the origami to do the folding and what their applications that turn out in the real world. It's not only for art's sake, it has an application in the real world. This video will show you what that is. All right? So, be quiet and watch this video.
My talk is flapping birds and space telescopes, and you would think that should have nothing to do with one another, but I hope by the end of these 18 minutes, you'll see a little bit of a relation. It ties to origami. So let me start. What is origami? Most people think they know what origami is. It's this: flapping birds, toys, cootie catchers, that sort of thing. And that is what origami used to be. But it's become something else. It's become an art form, a form of sculpture. The common theme, what makes it origami, is folding, is how we create the form. Now, it's very old. This is a plate from 1797. Shows these women playing with these toys. If you look close, it's this shape called a crane. Every Japanese kid learns how to fold that crane. So this art has been around for hundreds of years, and you would think something that's been around that long, so restrictive, folding only, everything that could be done has been done a long time ago. And that might have been the case, but in the 20th century, a Japanese folder named Yoshizawa came along, and he created tens of thousands of new designs, but even more importantly, he created a language, a way we could communicate, a code of dots, dashes, and arrows. Harkening back to Susan Blackmore's talk, we now have a means of transmitting information with heredity and selection, and we know where that leads. And where it has led in origami is to things like this. This is an origami figure. One sheet, no cuts, folding only, hundreds of folds. This too is origami, and this shows where we've gone in the modern world. Naturalism, detail, you can get horns, antlers, even if you look close, cloven hooves. Now it raises a question, what changed? What changed is something you might not have expected in an art, which is math. That is, people applied mathematical principles to the art, to discover the underlying laws, and that leads to a very powerful tool. The secret to productivity in so many fields and in origami is letting dead people do your work for you. Because what you can do is take your problem and turn it into a problem that someone else has solved and use their solutions. And I want to tell you how we did that in origami. Origami revolves around crease patterns. A crease pattern shown here is the underlying blueprint for an origami figure. And you can't just draw them arbitrarily. They have to obey 4 simple laws. And they're very simple, easy to understand. The first law is 2 colorability. You can color any crease pattern with just 2 colors without ever having the same color meeting. The directions of the folds at any vertex, the number of mountain folds, the number of valley folds, always differs by 2. 2 more or 2 less, nothing else. If you look at the angles around a fold, you find that if you number the angles in a circle, all the even numbered angles add up to a straight line. All the odd numbered angles add up to a straight line. And if you look at how the layers stack, you'll find that no matter how you stack folds and sheets, a sheet can never penetrate a fold. So that's 4 simple laws. That's all you need in origami. All of origami comes from that. And you'd think, can 4 simple laws give rise to that kind of complexity? But indeed, the laws of quantum mechanics can be written down on a napkin, and yet they govern all of chemistry, all of life, all of history. If we obey these laws, we can do amazing things. So in origami, to obey these laws, we can take simple patterns like this repeating pattern of folds called textures, and by itself, it's nothing. But if we follow the laws of origami, we can put these patterns into another fold that itself might be something very, very simple, but when we put it together, we get something a little different. So this fish, 400 scales, again, it is one uncut square, only folding. And if you don't want to fold 400 scales, you can back off and just do a few things and add plates to the back of a turtle or toes. Or you can ramp up and go up to 50 stars on a flag with 13 stripes. And if you want to go really crazy, 1,000 scales on a rattlesnake. And this guy's on display downstairs, so take a look if you get a chance. The most powerful tools in origami have related to how we get parts of creatures. And I can put it in this simple equation. We take an idea, combine it with a square, and you get an origami figure. What matters is what we mean by those symbols. And you might say, can you really be that specific? I mean, a stag beetle, it's got 2 points for jaws, it's got antennae. Can you be that specific in the detail? And yeah, you really can. So how do we do that? Well, we break it down into a few smaller steps. So let me stretch out that equation. I start with my idea. I abstract it. What's the most abstract form? It's a stick figure. And from that stick figure, I somehow have to get to a folded shape that has a part for every bit of the subject, a flap for every leg. And then once I have that folded shape that we call the base, you can make the legs narrower, you can bend them, you can turn it into the finished shape. Now the first step, pretty easy. Take an idea, draw a stick figure. The last step is not so hard, but that middle step, going from the abstract description to the folded shape, that's hard. But that's the place where the mathematical ideas can get us over the hump. And I'm going to show you all how to do that so you can go out of here and fold something. But we're going to start small. This base has a lot of flaps in it. We're going to learn how to make one flap. How would you make a single flap? Take a square. Fold it in half, fold it in half, fold it again, till it gets long and narrow, and then we'll say the end of that, that's a flap. I could use that for a leg, an arm, anything like that. What paper went into that flap? Well, if I unfold it and go back to the crease pattern, you can see that the upper left corner of that shape is the paper that went into the flap. So that's the flap, and all the rest of the paper is left over. I can use it for something else. Well, there's other ways of making a flap. There's other dimensions for flaps. If I make the flap skinnier, I can use a bit less paper. If I make the flap as skinny as possible, I get to the limit of the minimum amount of paper needed. And you can see there, it needs a quarter circle of paper to make a flap. There's other ways of making flaps. If I put the flap on the edge, it uses a half circle of paper. And if I make the flap from the middle, it uses a full circle. So no matter how I make a flap, it needs some part of a circular region of paper. So now we're ready to scale up. What if I want to make something that has a lot of flaps? What do I need? I need a lot of circles. And in the 1990s, origami artists discovered these principles and realized we could make arbitrarily complicated figures just by packing circles. And here's where the dead people start to help us out. Because lots of people have studied the problem of packing circles. I can rely on that vast history of mathematicians and artists looking at disk packings and arrangements, and I can use those patterns now to create origami shapes. So we figured out these rules whereby you pack circles, you decorate the patterns of circles with lines according to more rules. That gives you the folds. Those folds fold into a base. You shape the base, you get a folded shape, in this case, a cockroach. And it's so simple. It's so simple that a computer could do it. And you say, well, how simple is that? But computers, you need to be able to describe things in very basic terms. And with this, we could. So I wrote a computer program a bunch of years ago called Tree Maker. And you can download it from my website. It's free. It runs on all the major platforms, even Windows. And you just draw a stick figure, and it calculates the crease pattern. It does the circle packing, calculates the crease pattern. And if you use that stick figure that I just showed, which you can kind of tell it's a deer, it's got antlers, you'll get this crease pattern. And if you take this crease pattern, you fold on the dotted lines, you'll get a base that you can then shape into a deer with exactly the crease pattern that you wanted. And if you want a different deer, it's not a white-tailed deer, but you want a mule deer or an elk, you change the packing and you can do an elk. or you could do a moose, or really any other kind of deer. These techniques revolutionized this art. We found we could do insects, spiders, which are close, things with legs and wings, things with legs and antenna, and if folding a single praying mantis from a single uncut square wasn't interesting enough, then you could do two praying mantises from a single uncut square. She's eating him. I call it snack time. And you can do more than just insects. This you can put details, toes and claws. Grizzly bear has claws. This tree frog has toes. Actually, lots of people in origami now put toes into their models. Toes have become an origami meme because everyone's doing it. You can make multiple subjects. So these are a couple of instrumentalists. The guitar player from a single square, the bass player from a single square. And if you say, well, but a guitar, bass, that's not so hot, do a little more complicated instrument, well, then you could do an organ. And what this has allowed is the creation of origami on demand. And so now people can say, well, I want exactly this and this and this, and you can go out and fold it. And sometimes you create high art, and sometimes you pay the bills by doing some commercial work. But I want to show you some examples. Everything you'll see here, except the car, is origami.
Mitsubishi Endeavor. With a powerful 3.8-liter V6 and available all-wheel drive, a mythic combination of beauty and beast. Mitsubishi, driven to thrill.
Just to show, this really was folded paper. Computers made things move, but these were all real folded objects that we made. And we can use this not just for visuals, but it turns out to be useful even in the real world. Surprisingly, origami and the structures that we developed in origami turn out to have applications in medicine, in science, in space, in the body, consumer electronics, and more. And I want to show you some of these examples. One of the earliest was this pattern, this folded pattern, studied by Koryo Miura, Japanese engineer. Studied a folding pattern, realized this could fold down into an extremely compact package that had a very simple opening and closing structure. And he used it to design this solar array. It's an artist rendition, but it flew in a Japanese telescope in 1995. Now, there is actually a little origami in the James Webb Space Telescope, but it's very simple. The telescope is going up in space. It unfolds in two places. It folds in thirds. It's a very simple pattern. You wouldn't even call that origami. They certainly didn't need to talk to origami artists. But if you want to go higher and go larger than this, then you might need some origami. Engineers at Lawrence Livermore National Lab had an idea for a telescope much larger. They called it the eyeglass. The design called for geosynchronous orbit, 25,000 miles up, 100-meter diameter lens. So imagine a lens the size of a football field. There were two groups of people who were interested in this: planetary scientists who want to look up, and then other people who wanted to look down. But whether you look up or look down, how do you get it up in space? You got to get it up there in a rocket, and rockets are small. So you have to make it smaller. How do you make a large sheet of glass smaller? Well, about the only way is to fold it up somehow. So we have to do something like this. This is a small model, folded lens. You divide up the panels, you add flexures, but this pattern's not going to work to get something 100 meters down to a few meters. So the Livermore engineers, wanting to make use of the work of dead people or perhaps live origamists, said, let's see if someone else is doing this sort of thing. So they looked into the origami community, got in touch with them, and I started working with them. And we developed a pattern together that scales to arbitrarily large size, but that allows any flat ring or disc to fold down into a very neat compact cylinder. And they adopted that for their first generation, which was not 100 meters, was a 5 meter. But this is a 5 meter telescope, has about a 1/4 mile focal length, and it works perfectly on its test range, and it indeed folds up into a neat little bundle. Now, there is other origami in space. Japan Aerospace Agency flew a solar sail, and you can see here that the sail expands out, and you can still see the fold lines. The problem that's being solved here is something that needs to be big and sheet-like at its destination, but needs to be small for the journey. And that works whether you're going into space or whether you're just going into a body. And this example is the latter. This is a heart stent developed by Chong Yu at Oxford University. It holds open a blocked artery when it gets to its destination, but it needs to be much smaller for the trip there through your blood vessels. And this stent folds down using an origami pattern based on a model called the water bomb base. Airbag designers also have the problem of getting flat sheets into a small space, and they want to do their design by simulation. So they need to figure out how in a computer to flatten an airbag. And the algorithms that we developed to do insects turned out to be the solution for airbags to do their simulation. And so they can do a simulation like this. Those are the origami creases forming, and now you can see the airbag inflate and find out, does it work? And that leads to a really interesting idea. Where did these things come from? Well, the heart stent came from that little blow-up box that you might have learned in elementary school. It's the same pattern called the water bomb base. The airbag flattening algorithm came from all the developments of circle packing and the mathematical theory that was really developed just to create insects, things with legs. The thing is that this often happens in math and science. When you get math involved, problems that you solve for aesthetic value only, just or to create something beautiful, turn around and turn out to have an application in the real world. And as weird and surprising as it may sound, origami may someday even save a life. Thanks. My talk is flapping birds and space telescopes.
So you see how far they can go. Am I right? This, yes? I'm not asking the question, okay? Now, okay, let me wrap up this whole thing here then, okay, for today. I think you've been here long enough. Before I let you go off, let me ask you a question. Why do we learn mathematics? Because of what? You're forced to learn. You're forced to learn. Okay. Do you see math is real in everyday life? Can you live in this world without mathematics? No. That's why you learn mathematics. See? That's the reason why you do learn mathematics. Now let me share with you. There's one expert telling us why we find math is difficult to learn. Okay? And this is a little thing, and let me wrap it up then for you here. Watch out. This is an American professor. Watch out what he says. Listen to him.
So why do we learn mathematics? Essentially for three reasons: calculation, application, and last, and unfortunately least in terms of the time we give it, inspiration. Mathematics is the science of patterns, and we study it to learn how to think logically, critically, and creatively. But too much of the mathematics that we learn in school is not effectively motivated. And when our students ask, why are we learning this? And they often hear that they'll need it in an upcoming math class or on a future test. But wouldn't it be great if every once in a while we did mathematics simply because it was fun or beautiful or because it excited the mind? Now, I know many people have not had the opportunity to see how this can happen. So let me give you a quick example with my favorite collection of numbers, the Fibonacci numbers.
Again, is the Fibonacci.
Yeah, I already have Fibonacci fans here. That's great. Now, these numbers can be appreciated in many different ways. From the standpoint of calculation, they're as easy to understand as 1 plus 1, which is 2. Then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Indeed, the person we call Fibonacci was actually named Leonardo of Pisa, and these numbers appear in his book, Liber Abaci, which taught the Western world the methods of arithmetic that we use today. In terms of applications, Fibonacci numbers appear in nature surprisingly often. The number of petals on a flower is typically a Fibonacci number, or the number of spirals on a sunflower or a pineapple tends to be a Fibonacci number as well. In fact, there are many more applications of Fibonacci numbers, but what I find most inspirational about them are the beautiful number patterns they display. Let me show you one of my favorites. Suppose you like to square numbers. And frankly,
watch
who
out here, the
doesn't?
square the number for Fibonacci numbers.
Let's look at the squares of the first few Fibonacci numbers. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, and so on. All right, now, it's no surprise that when you add consecutive Fibonacci numbers, you get the next Fibonacci number, right? That's how they're created. But you wouldn't expect anything special to happen when you add the squares together. But check this out. 1 plus 1 gives us 2, and 1 plus 4 gives us 5. And 4 plus 9 is 13, 9 plus 25 is 34, and yes, the pattern continues. In fact, here's another one. Suppose you wanted to look at adding up the squares of the first few Fibonacci numbers. Let's see what we get there. So 1 plus 1 plus 4 is 6. Add 9 to that, we get 15. Add 25, we get 40. Add 64, we get 104. Now look at those numbers. Those are not Fibonacci numbers, but if you look at them closely, you'll see the Fibonacci numbers buried inside of them. You see it? I'll show it to you. 6 is 2 times 3, 15 is 3 times 5, 40 is 5 times 8, 2, 3, 5, 8. Who do we appreciate? Fibonacci, of course. Now, as much fun as it is to discover these patterns, it's even more satisfying to understand why they are true. Let's look at that last equation. Why should the squares of 1, 1, 2, 3, 5, and 8 add up to 8 times 13? I'll show you by drawing a simple picture. All right, we'll start with a 1 by 1 square, and next to that, put another 1 by 1 square. Together, they form a 1 by 2 rectangle. Beneath that, I'll put a 2 by 2 square, and next to that, a 3 by 3 square. Beneath that, a 5 by 5 square, and then an 8 by 8 square, creating one giant rectangle, right? Now, let me ask you a simple question. What is the area of the rectangle? Well, on the one hand, it's the sum of the areas of the squares inside it, right? Just as we created it. It's 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared, right? That's the area. On the other hand, because it's a rectangle, the area is equal to its height times its base. And the height is clearly 8, and the base is 5 plus 8, which is the next Fibonacci number, 13, right? So the area is also 8 times 13. Since we've correctly calculated the area 2 different ways, they have to be the same number. And that's why the squares of 1, 1, 2, 3, 5, and 8 add up to 8 times 13. Now, if we continue this process, we'll generate rectangles of the form 13 by 21, 21 by 34, and so on. Now, check this out. If you divide 13 by 8, you get 1.625. And if you divide the larger number by the smaller number, then these ratios get closer and closer to about 1.618, known to many people as the golden ratio, a number which has fascinated mathematicians, scientists, and artists for centuries. Now, I show all this to you because, like so much of mathematics, there's a beautiful side to it that I fear does not get enough attention in our schools. We spend lots of time learning about calculation, but let's not forget about application, including perhaps the most important application of all, learning how to think. If I could summarize this in one sentence, it would be this. Mathematics is not just solving for X, it's also figuring out why. Thank you very much.
Oh, it's not about solving equations. Ask why I'm doing it this way or that way. You see, mathematics is to develop your thinking skills, not so much the math content. Thinking skills, problem skills is not confined to only mathematics. I call that what? Life skills. Why? Because you can use it in other areas. The same strategies, the same skills that you learn in mathematics can be used in science, even in humanity courses. Well, that very matter there. So bear in mind that, math is everywhere. It's not only in science. No, sorry. It's everywhere. Even next time when you take any humanity courses, you need mathematics. You take economics, you need mathematics. To be honest. So bear in mind, it has a wide application there. By the way, do you realize that what you have done just now, some of the activities is actually in the A-math? You can do A-math actually. You already try out, you prove yourself. This is only a brief introduction to what you can do. So don't be too afraid of the A-math. Oh, it's so difficult. It is not. It is only an extension of your E-math, what you have learned. So, you think about that. I will encourage you to take up, the challenge here. I tell you what, if you have both A and E-math, when you go out to a higher level, I don't care what you take for your higher education, whether you go into STEM courses or non-STEM courses there, you will find that it's an asset that you can use it. But bear in mind, math is not about the content. It's about what? Developing your thinking skills and problem solving skills. So that is the important point I want you to bear in mind there. Okay? Yeah, thank you very much, for here today, and hope there's some fun.